I'm Brian Acosta and I'll be doing question 10.
All right, question 10. How many grams of participate are formed when 12.5 milliliters of 1.23 molar calcium chloride reacts with excess potassium phosphate? So immediately looking at this problem, you're going to have to know a few things. Calcium chloride is written as such, calcium 2 chloride, and potassium phosphate is written as K3PO4. The way you find the exact values for this is that you should know is that PO4 has a value of -3. And if you look at your periodic table, calcium has a value of +1. So from there, it goes by group, by the way. So you wouldn't be able to actually tell from the actual logo of potassium on the periodic table. But anyways, moving on. So from here, the next thing I'm going to want to do is probably create a formula for the actual reaction itself. So calcium chloride plus the potassium phosphate, it will create our products here. From here, whenever you're doing this is like a double replacement reaction, the cations or the positive ions will separate from the anions and they will switch places. So if you take a look, this calcium will now be with the phosphate and the potassium will be with the chloride. So the way we know to add these subscripts and everything is from the charge of the actual cations and anions themselves. So phosphate you should just have memorized, it's -3. And calcium, if you look at your periodic table, is in the second group, which means it's willing to lose 2 electrons. So coming back here, its charge is a +2. And from there, we can just come up with their subscripts. One way I like to think about it is since it originally was a +2, and I put a subscript of 3, now it's a +6. And now if you look at this phosphate, it's originally a -3, but since there's 2 of them because of the subscript, it's a -6. +6 -6, you have a neutral, which means it works. You're not breaking any laws or doing illegal chemistry. So if you look here, this is another simple one. This is just the first group cation and right there. So this is just +1, and chloride is towards the end, which is -1. So therefore you put them together and you're good. I'll cover how I wrote aqueous here and non-aqueous or solid and a little bit further down. So from here, you're going to want to balance the equation. So you got, just look at your amounts on each side. So you got calcium, you got chloride, you got potassium, and you got phosphate. So what I like to do is I like to write all of what I have right here. And you see this right here is for every element on the left side and every element on the right side. And from there, I just put some coefficients in front and try to get the left side to equal the right side. And after you balance that equation, you should come out with this exact equation right here. So from here, I'm going to go ahead and address the aqueous versus non-aqueous or solid form of each part. So looking at the solubility chart. So this is this chart, should be included. And looking at every single one of these compounds, chloride is right here on this chart. See, we're going to see chloride. It's going to be soluble ionic compounds, which means that if it is not one of these exceptions, it will be soluble, which means compounds with silver, let's see, mercury and lead. I believe that's mercury, don't quote me on that. And if we look at here, calcium chloride is not an exception. Therefore, it is soluble and it is aqueous. Looking at phosphate here, phosphate is a insoluble, which means it will not dissolve. That's why. But if you look at the exceptions, it will dissolve when combined with a group 1 cation or an ammonium ion. So looking at this one, potassium, if you look at your periodic table, is a group 1 cation. So it is an exception, it will dissolve. And that's why you write aqueous here. Going through the same process, just looking at phosphate, and then with right here, phosphate, and seeing that it is not calcium, which is what it's combining with, is not an exception. See, that's why it is solid. And then chloride, which is right here, it is combining with potassium this time, and that's not an exception, so therefore it is soluble, and that's why I write solid and aqueous here. All right, so now that we got all that out of the way, we should be able to do some simple math and figure out our answer. So they give us 12.5 milliliters of 1.23 molar calcium chloride, and this potassium phosphate is in excess. So we know this is our limiting reagent right off the bat. Come down here, the formula for molarity is molarity equals moles over liters. They give us 1.23 molar calcium chloride. From here, we're going to plug that into our formula, and we see that they gave us milliliters, which is, we need liters for this formula. So using a little simple conversion factor, you can figure out that 12.5 milliliters is converted to 0.0125 liters. Plug that into the formula, and we can multiply that over and calculate 0.0154 moles of calcium chloride. From here, we're going to just reference our equation again and see that for every 3 calciums of calcium chloride, we're going to produce 1 mole, or for every 3 moles of calcium chloride, sorry about that, we'll produce 1 mole of calcium phosphate. So the reason why also this question is asking for the precipitate, which means we're not interested in this aqueous product, we're only interested in this solid product, and that's why I chose this. So coming here, we're just going to put exactly what I just said into a little simple conversion here, and using the moles we calculated before, we're just going to, for every 1 mole of calcium phosphate produced, we use up 3 moles of calcium chloride. Do some simple math here, and you get this amount of moles, 0.005125 moles of calcium phosphate. And of course, that's just the solid we addressed earlier. From there, we get that molar account, and this, we're just going to do a molar mass to convert the moles to grams of this, and this is just to take another quick trip to our periodic table here, and you can just see the actual weight of calcium here, 40.08, the weight of phosphorus, and the weight of oxygen. Now, don't be fooled. You're not just going to grab these weights by themselves. You're also going to multiply them by the subscripts, which is calcium, which is a 3 here, and this 2 means that phosphate is also a 2, and oxygen is now an 8, because it has a 4 on the inside, 2 on the outside, that's 8. So using those numbers we got from our periodic table, multiply them out, add them together, and we get the molar mass of this specific compound is 310.18 grams. From there, we convert from moles, doing some simple math, and we'll get the exact amount of grams produced, which is our answer.